Hello, my name is Jonathan Apostle, and this is my fifth lab for Physics 2212. And in the comments of the YouTube video, there should be different timestamps for each of the points in the rubric. Within this lab, I will start by looking at the introduction and some conclusions that I drew. Next, I'll be looking at some key assumptions and formulas, then move on to the methods and glow script that we used, and then finally going back to those conclusions and then also answering the what if and what does it mean questions. So for the introduction, I'm also going to make sure to include a preview of the main results. So the purpose of this lab was to collect time data for a falling magnet while moving through a tube of conductive aluminum foil. Therefore, we can find a time derivative, getting the magnetic flux. So what are some fundamental principles? Well, there's going to be Newton's second law, so the force generated by the magnet moving through that tube is going to be in the opposite direction to gravity. Also, we have to realize that induced current is a thing. So this ties in Faraday's law and also Lorentz's formulas as well. From this, we can compare our observed results to a computational model to see how they differed, so taking into account any potential human error. Just to go back to those previews of the results, magnet falls through the tube, therefore it was able to be slowed when it exited, and this was also confirmed in the glow script model. So going back to the key assumptions and formulas, and therefore the main physics ideas of this lab. A key assumption is that the only force acting on the magnetic ball upon release, not during the tube, but upon release, was gravity. Afterwards, there's going to be that force generated by the moving magnetic flux as the magnet moves down the tube. And this again is a direct application of Faraday's law, Lenz's law, and also with getting the force, the Lorentz force equations. And just looking at some key formulas, I've listed them here. This is Faraday's law, and then Lenz is going to tie directly into this, and then the Lorentz force for that moving charge. And therefore, when given the resistivity of aluminum, that's another key assumption that we need to take into account as well. One of the good parts about this lab is that the methods are very straightforward. So you just drop the ball through and you see how much time it took for it to completely fall. So as you can see, I dropped the ball, there's a force of gravity acting on it, and there's going to be a force that's induced, which is going to be the electric force from the magnetic flux. Here are my measurements. I measured that the length of the tube was 0.35 meters, the radius was 0.006 meters, and therefore the mu constant, which again we are given, is 3.21, and then the mass of the magnet was roughly 0.025 kilograms, and the time of the fall was about 1.3 seconds. And this is me dropping the magnet down the aluminum tube. And I would feel bad if I didn't explicitly state the system and surroundings. So the system in this instance is that magnetic ball, which again is functioning like a dipole. And then the surroundings would be everything else. And it does include that aluminum tube. And some more initial conditions are that the magnet falls down from 0 and hits the ground at the stop time. Also, there are no other forces acting on the magnet. And this is that glow script code that I was talking about beforehand. So the key aspects here were just to do the resistivity, and then obviously the force of gravity, which is constant on Earth, and then the mu naught over pi value, which we were given. And then I just plugged in all the values in terms of the actual tube, and then just graphed them as a visualization. Most of this information was just given to me already. And then when I run it, as you can see, the magnet falls. And afterwards, the time was 1.394 seconds. I know there's a lot of information on this slide, but I'm going to try and go through this pretty quickly. So some similarities, there was a relatively high percent error. However, the overall trend was correct. Therefore, we did see that there was a magnetic force that was generated by a current, and that the current was induced by a changing magnetic flux. The error prediction for this would probably be that there was a slight resistance that I kind of pushed it down a little bit. And that was a key aspect of this model, was that I was assuming that the only force acting on it was gravity. Interpreting the simulation, this was included in the lab report, so I just wanted to go through these real quick. The colors, they're going to be the positive current will be in the red and the negative will be in the blue. And then what if the magnet is flipped? It's going to be equal and opposite, so the direction is going to change, but the actual magnitude will not. How does the time compare to the system, and how can the computational model be more accurate? Again, looking at this more so as a perfect dipole would be really not an entirely accurate way to view it, because it is slightly wobbling. And how does the shape of the velocity time tell us more about the forces? And the key aspect here is it's going to reach that potential terminal velocity. So if the tube is long enough, it's going to eventually hit this terminal velocity, but there's going to be no net force acting on it. What if and what does it mean questions? If the resistance was greatly reduced, that means that the current would increase, thus the force would directly increase as well. And then if the holes were cut in the tube, then this is kind of like breaking a circuit, so it would greatly disrupt the entire current that was going through it, and therefore generally weaken the amount of force that the magnet would be able to resist that fall. So for the introduction, I looked at Faraday's law and the laws of inductance. The system was the magnet and the surroundings the aluminum tube and the earth. The models and main physics ideas are Faraday's law, Lorenz's force, and Lenz's law. As I dropped the magnetic dipole through an aluminum tube, inducing a charge, therefore I could see how long it took to land and compare this to a glow script model. And just to recap everything, there was a clear correlation, yet there was slight human error, and I also made sure to answer the what if and what does it mean questions.